cooling. So during this operation, what are the changes, physical or chemical changes is happening in the sample, that is being studied in thermal analysis, or that is being called thermal analysis. So in that monitoring purpose, or what are the changes is happening, so there are few parameters which are being monitored in the sample. So one is a mass property, and for that the technique is known as thermogravimetric analysis, or the short form is TGA, where we basically monitor the change of mass of the substance against temperature. The next one is enthalpy. That is, the technique is known as differential scanning calorimeter. Here, basically, we measure the enthalpy or the heat amount. So that means when we are heating or cooling, or we are keeping some sample in isothermal mode. So if there is any changes, or system is taking any heat, or taking in some heat, or leaving out the heat, so that measurement is done in DSC. Then there is another technique which is a combination of mass and enthalpy. So that is called simultaneous thermal analysis, or TGDTA. We call it STA. So in that also, at the along with the changes of mass in the sample, you can also measure the heat flow into the system using this instrument, that is called simultaneous thermal analysis. And one more instrument and technique is there, where we monitor the viscoelastic properties of the substance, and that technique is known as dynamic mechanical analysis, or the DMA. So PerkinElmer is having all the instruments like TGA, DSC, STA, and DMA. So first we will go through this thermogravimetric analysis. So this is thermogravimetric analysis, where we measure the change in mass of a sample or weight of a sample as the sample is heated or cooled or held at constant or isothermal temperature. So here you can see so this is a classical thermogram of a substance where it has been analyzed in TGA, where the system has run from 50 to 700 degrees Celsius. And here you can see the different transition which is occurring at different temperature. So the volatiles are getting lost around 150, 170, then oil extender, polymer, or carbon. This is how any kind of TGA thermogram looks like for any sample, where we control the sample atmosphere. So at the same time, along with heating or cooling or isothermal, the sample can be taken in different atmospheric condition. Like you can use different type of gases like nitrogen, argon, helium, oxygen, and as per the application requirement, and you can monitor the changes. And this gas is also a very critical factor for TGA, because that will, if there is any interferences from unwanted gases or any leakage, so that may hamper. So that also need to be taken care. So this is basically a compositional analysis, the TGA. So the model which we have supplied here is called a TGA 8000 model, which is a high sensitivity ultra micro balance we have in this. And in TGA, as we are having this, we are measuring the weight loss. So that weight loss is being measured using a micro balance, which is there inbuilt in the system. So here the different systems, different models are using different kind of balance. But here in TG 8000, we are using a micro balance, and which is highly sensitive. Then we have this low mass motor controlled furnace. So here the furnace is controlled by, it is a motorized control operated by the software. You don't need to manually move the furnace up and down. All this movement is done by using a stepper motor, and it can be controlled by the software. Just on a click on a button on the software, this furnace will go up and down. Also, we have the auto sampler capability of 45 position, that is also you are using. So there you can put the sample in unattended condition, and you can define the program in the software where one by one sample will be put in the furnace, and it will be analyzed, then it will be taken back, and the next sample will be put like that. Also additionally, we have this iPad and iPhone connectivity with local control. we have the built-in mass flow controller. Why mass flow controller is required? Because the sample purge gases which we are using for different kind of application like nitrogen, helium, argon, oxygen. So we need to control the flow rate very precisely. So this mass flow controller controls the flow rate of the gases very precisely, and you can define the flow rate of the gas through the software which is being controlled by this this software will also control this mass flow controller. And also this system is designed for hyphenation as I was talking. So that is a coupling of another system. So this evolved gas analysis in future, if you would like to upgrade the system for TGIR or TGGCMS or TGIR GCMS kind of hyphenation, so that is also possible with this TG8000 model. And we have the highest productivity, the best autosampler and fastest furnace in that model designed for hyphenation for evolved gas analysis. So this is the balance part, which is the core for any TGA, not only a TGA 8000. If you are working with any other TGA, the very, very important part is balance, and that will define the sensitivity of the system. Because here we are only measuring the change in the weight of the sample, nothing else. So that may be in terms of absolute mg value or the weight percentage loss from 100%, how much percent is losing. So for that purpose, the that measurement is done by this balance. So balance sensitivity, balance construction, and balance durability is most important part of the any TGA instrument. So here we are using basically a null restoring principle balance, proven high performance design. So this is basically a hanging balance where there is a electronic signal is there which works as a null position balance. So if there is any changes in the weight, so that will send some signal to the balance to bring it to the null position, and whatever be the changes is there, that is actually proportional to the weight change. So that is the principle, any null restoring principle balance. And this is a hang down balance for which the sensitivity is very, very high, that is 0.1 microgram is the balance sensitivity which is there in this TG8000 model. Also the temperature monitored for drift compensation in calibration. So there is also a terminology called balance drift. So that means when there is no sample or nothing is there in the balance, there may be some little change in the weight or weight percentage is observed in different balances. So that will ultimately affect your sample analysis. So controlling the drift and calibrating the instrument for proper in sample analysis is also very, very important. So here also we are using this temperature monitor for the drift compensation at different temperature and doing the calibration accordingly during the installation. So that is being taken care by our service team. So how the TGA balance works, this is basically a null balance. When a sample is placed on the pan, the beam flag deflects momentarily, causing a change in the current. So the current is fed back to the torque motor to restore the beam to its original position. And the current required to restore this beam is the sample weight. So this is a direct measurement. So there is no chance of error, and hardly there is any chance of getting any erroneous value from this type of design. And this is the little bit of the features and specification and the capability of the TG8000 model which you are using in your lab. So this is a vertical TGA design with high sensitivity of balance, which I already told, that is 0.1 microgram is the sensitivity. So if there is any little change in your sample, example like the moisture content in pharmaceutical sample or drugs, the content of moisture is at the trace level in the pharmaceutical samples. So it is not possible to monitor those changes of that trace level of moisture with using a system where the balance sensitivity is around 1 microgram, because that changes comes in first decimal of microgram, that is less than 1 microgram. So you need to have a system which can measure the changes at the range of 0.5, 0.6 microgram weight. So this system is capable for that. Also broad weight range, that is 1300 mg to better representation of sample size, that is 1.3 gram is the maximum balance capacity. But we usually recommend the sample weight to be taken in between 5 to 10 mg, because you don't know whether there will be any flotation or any kind of what you call this spillage will be there from the sample or not. So if so the spillage or any kind of this
Excuse
incident
me,
occurs.
Kaushikji.
Hello. Yeah.
Yeah, here, what is the minimum weight frequently we can use?
Ma'am, normally it's 5 to 10 mg.
But
Let me go
less
through the
than five.
presentation. Ma'am,
Okay.
just let me complete the presentation,
Okay, okay,
then
okay,
we
okay.
can have the
Yeah.
QA session for all your
Okay, okay, okay,
queries,
okay,
because
okay.
Sachin is
You
also
okay?
there,
Okay,
so we
okay. You can
can resolve
continue.
all the
Okay.
query. Yeah, yeah.
Okay.
Thank you, ma'am. So this is the maximum capacity recommended is 5 to 10, and that we can discuss in our QA session for your kind of sample and application. And temperature range of this instrument capable is -20 to 1200 degrees Celsius with optional chiller and sub-ambient kit. But hardly we use TGA for any sub-ambient application. So majorly, mostly it starts from RT, and basically we measure the changes in terms of heating. So this system can go up to 1200 degrees Celsius with a fastest heating rate of 500 degrees Celsius per minute. So that means when you are creating or developing your method for TGA method for your sample analysis, so you have the option to define the heating rate. Normally, we kept the heating rate of 10 to 20 degrees Celsius, but if you want to see any fast change or kinetics type of study or any specific application demand, where because normally any other TGA can go up to maximum 200 degrees Celsius per minute, not more than that. But here in this system, you can go up to a rapid heating of 500 degrees Celsius per minute. Then motorized lowering and raising of the furnace for better precision. So you don't need to do any manual intervention, so that there may be some drift issue or some other unwanted effect may affect your sample analysis. So that has been taken care by the motorized lowering and raising of the furnace through the software. Low mass furnace we are using for fastest cooling down and productivity less than 13 minutes. So that means from 1000 to 100 it will come down within 13 minutes. So that will increase the productivity of your system, because usually you have seen the thermal event is a time consuming event rather than any spectroscopic experiment or other. So any thermal experiment will last for around 30, 40 or even 50 minutes or more than hour, depending on the temperature and the heating rate you have defined. So for the next sample, again the system has to cool down, come to the room temperature, then only you can start the second sample analysis. So this cooling down, if not faster, then again your unproductive time will increase in the lab. So that is being taken care in this system. So it is only the 13 minutes which for which the system will come from 1000 to 100 degrees Celsius. Integrated mass flow controller. This is mainly required for the precise flow of the purge gases which you are using for your sample. Normally in the system by default we have nitrogen purging for the system purge, so that no corrosive gases will enter into the balance part and damage it. So that is there. Apart from this system purge, you can have different type of sample purge like oxygen, hydrogen, helium, nitrogen as per the application requirement, and there you can define the exact flow rate of the gases as per your method or as per your application requirement. So there we are using the mass flow controller. Wide range of gases purging can be possible. Built-in forced air cooling for faster turnaround. This is the system where for normal operation you don't need any chiller, because other any other TGA chiller is required for the operation for the cooling down, but we have a forced air cooling design in this model for which you don't need to add the additional chiller. All advanced software integrated with the unit. We have different features in the Pyris software which is being provided with the instrument, and For your information, this Pyris software is common for all Perkinelmer thermal instrument like TGA, DSC, STA, DMA. So whatever be the instrument you have, this is the single software platform which will enable you to control all the system and work. So you don't need to learn different software for different instrument. And all magnetic Curie transition material for accurate calibration of temperature. This is already done by our engineer during installation. If next time any calibration is required, so that will be also done using this magnetic Curie transition material. For that is the standard or universal standard which is used for temperature calibration. Hyphenation to spectrum to frontier MS and GCMS. So this is the upgradation capability of this model. So in future, if you want to measure the evolved gas analysis coupling with FTIR or GCMS, so that also possible. And the 48 position auto sampler, which is already there in your lab along with the system for unattended operation. And this is the internal design of this instrument. So how does it work? So this is the system part which is goes to the balance unit, so that any corrosive gases which is coming from the sample cannot affect the balance chamber. And there we have two sample parts, A and B, which is controlled by the MFC, which is going to the furnace directly. So here you can connect different gases as per your requirement, like nitrogen, oxygen, helium. And this is reactive part, not internal MFC. This is the additional port we have given for any specific application of reactive part. And sample temperature control is platinum owned ceramic microfurnace with 20 to 1200 degrees Celsius. As because we are using this platinum owned ceramic microfurnace, so heating and cooling rate is faster, and at the same time the heat measurement capacity or sensitivity is also very high. And also it's a long lasting and durable material which will go for long run of your analysis. Thermocouples are close to sample which will monitor the changes in temperature of the sample, that what is the actual sample temperature that is being measured by the thermocouple. Scan rate is 0.1 to 500 degrees Celsius, but normally in TGA we keep this heating rate at 10 to 20 degrees Celsius max. But if you want, the system has the capability to go up to 500. Superb isothermal stability. So if you have in between your heating, if you want to give any isothermal run, so there also you can see the baseline stability is very strong in this system. Motor used to raise the lower furnace, so that is also motorized. And purge gas environment, already I told that independent built-in mass flow controller and a reactive purge for fast gas environment changeover. That is introduction of oxygen. Suddenly, if you want to give any oxidation measurement of the sample, that is also possible. And this is the optional gas mixing device. Just for your information, in future, if you any application demands that you need to use a mixture of three gases or two gases into the system, so you can go for this GMD 8000 gas mixture, which will be again software controlled and can be connected with the TGA. Here you can see you can give three different gases which are controlled by MFC, that is the flow of these gases are very precise. And then there is a mixing chamber. After that you can give the output as per the combination as per your requirement. So that may be gas A or B or C, or the mixture of gas ABC. So this is the additional accessory which can be connected to this system for the precise mixing of gases. If it is a single gas environment for your application, you don't need it. But if you need to give any kind of mixture of gases, if you have any other mixing device, fine. Otherwise, this is the another option we have for this TG8000. And unsurpassed temperature control using heater sensor furnace technology. So five magnetic standards are supplied with TGA. We normally supply this alumel, cobalt, iron, nickel, and perc alloy. And we do the calibration of the system for the entire temperature range using this magnetic standards and this metal standards. And that is why you get the tight temperature control, temperature reproducibility, and separation accuracy. So here you can see the 4 runs of 4 QDs at 20 degrees Celsius. So all the data are almost 100% reproducible. There is hardly any difference it will found in between the 4 runs which has been done during the calibration procedure. And this is the auto sampler part already user using. I am not going into the much details of this. So this is the auto sampler where as per your setup program or manually also you can unload the sample as per the position defined in the software. So that position will go under the furnace and the hanging pan which is there is taken by the hang down wire and it will put in the furnace. Again during unloading you have to define the position, the blank position where you want to unload this sample pan in the auto sampler. So the system will precisely unload the pan in that particular position and then again you can give the command of loading of another sample which is the another position. And here also another thing is while if you are going for hyphenation connectivity in future, so this auto sampler will not hamper this hyphenation connectivity. Usually, normally in any other system, it has been seen that if auto sampler is there, then there is a challenges to connect the hyphenation transfer line. But here in TG 8000 with auto sampler can be connected with the hyphenation transfer line. Rapid cool down, already I informed that it is 13 minutes only, 1100 to 50 degree for your next sample analysis and utilizing of the instrument time, downtime. And one more additional feature or we can say a unique feature we have in this model. So normally what kind of operation is going on or at what stage of your method you are, you need to go to the monitor to understand that whether it is heating or cooling or isothermal. But here we have three different light coding seeing by viewing which you can understand that at what mode the system is working in. So that means if it is heating, you can see red light. When it is isothermal, it is green light, and if it is cooling, that is blue light. So every time you don't need to go in front of the system. From a certain distance, you can see the light and you can understand, okay, so this blue means the heating is done. So my system is cooling down. So now I can prepare the next sample for the loading. So this is the additional status indicator, illumination status indicator we have been provided in this TG 8000 model. And this is motorized furnace control that you are using already. And also you have seen when you are opening is continuous. So while closing the furnace, you have seen that the furnace first goes to some extent, it rests for few seconds, then it closes completely. That is mainly to eliminate any kind of buoyancy effect or anything or any gas flow effect which may disturbed the balance measurement of the measurement capacity of the microbalance, because before that you have done the weight tearing. So after that, when you are actually putting the sample, so there should not be any issue circumstances issue which may affect this measurement. So that has been taken care by this motorized design. And this is the hyphenation transfer line which we was talking about. In future, if you want, you can connect this kind of transfer line to directly measure the evolved gases which is coming from the sample. Because in TGA, what we do, a single TGA will only tell us about the weight percentage. But the information of the gases which is coming out from the sample is not known to us. So many application demands that these gases need to be identified. So you need to have a configuration where those gases can be transferred in gaseous mode to other equipment where you can analyze the gases. So normal TG analysis will tell you only just what are the composition in your sample. That is basically a compositional analysis. But what are the gases which is coming out from the sample is not known to you. So for that, you have this additional technique, or we have this technique where a TGA can be connected to a IR, MS. Now this we don't have, it is only TGA GCMS. And also there is another configuration where TGA is connected to a FTIR and it goes to a GCMS. So here FTIR and GCMS are the equipments which can measure the gases and identify the gases from which are coming from this heating of the sample in TGA. And PerkinElmer is the only company, for your information, because almost all of you are aware of this hyphenation technique or TGGCMS TGIR technique. But we are the only company who is having all the instrument manufactured by us. We have the TGA, we have FTIR, we have GCMS, and this transfer line is normal, is only manufactured is Redshift. We have a technical tie-up with them who are manufacturing this transfer line for our instrument compatibility. And these are the heated transfer line. The temperature range stays around 270 degrees Celsius, because to ensure the gases which are coming from your TGA will not get condensed. It will it will travel and gaseous mode only to FTIR or GCMS. In FTIR, there is a heated gas cell is connected where you can give the command that when the FTIR spectra of the gases to be taken. So, and the library, vapor phase library will help you to identify that if any higher active gases is there, what are the gases. And in GCMS, though, you know, it is the full-fledged analysis of the gases which is coming out from the TGA, where the separation will be done in GC, and then you will get the mass spectra of those gases, and using the NIST library, you can identify those gases while using the mass. So that is the advantage of PerkinElmer. We are the only manufacturer in the world who are having all the three instruments. We have the capability, we have the installation, we have the references, and the technical expertise to run a full-fledged hyphenation system. Because for any other vendor, either they are the manufacturer of the thermal part or the FTIR or the GCMS part. But for the coupling, they need to collaborate with another company to give a complete solution to the customer. And if any issue comes, then this blame game starts, that thermal company will say, no, we don't have any problem. It is maybe due to your FTIR or GCMS and vice versa. But we don't have any chance to blame any other cells, because we are the systems manufactured by us only. So that is the application and instrumentation part which are using. So now we will go through the application. So Sachin, shall I run through the slide, and will you carry on with from your laptop?
Anything, Kaushik, no
Okay,
problem.
okay. Okay, so let me run the slide. So now I welcome my colleague, Mr. Sachin Gajakosh. He is our senior application specialist stationed in Thane, and he is working in our Center of Excellence lab in Mumbai. So he will go through to the different applications of thermogravimetric analysis. Sachin, over to you.
Yeah. So, first of all, thank you, Kaushik.
Hello, Sachin.
Yeah,
Yeah, carry on.
I think just a minute. There
Yeah,
is a
yeah.
echo there.
No, for me, though, it's okay, perfect. I'm not getting any echo in your voice.
Okay. Uh, can you shut down your mic? Let me check.
Okay, just a minute.
Yeah. So first of all, yeah, now this is right. Okay. So first of all, thank you very much, Kaushik, for going through all the details of our instrument, our product portfolio, and how we can serve this industry or this analytical instrument industry with our different kind of product portfolio. So today, as Kaushik mentioned, that we are talking about the thermal instruments. So before that, I thank to IIT Patna faculties and all the team members for providing us this opportunity to showcase our capabilities for this kind of solutions from thermal analysis. So myself, Sachin Gajakos, and I'm based out of Mumbai. Uh, I'm associated with PerkinElmer for last 8 years. I'm from application department, and we are taking care of a lot of different things like developing applications here, training a different kind of people from inside or outside of our organization. So today we will see about the what are the applications can be done with the help of thermal product portfolio or the solutions we are offering from the PerkinElmer side. So before that, let us understand what is the thermoanalysis. So it is a term applied to a group of methods and techniques in which a chemical or physical property of a substance, a mixture of substance, or a reaction mixtures, they are measured as a function of temperature or time, while the substance are subjected to a controlled temperature program. So as we know, we in the lab or when we are working on any kind of samples, classically we mostly deal with the different kind of muffle furnaces or the different kind of ovens where we put our sample isothermally for particular time, and then we remove it and we check what is happening with the sample or what is happened with the sample or the changes in the sample. But this thermal product portfolio from our side, it actually give you that particular advantage to observe your sample, what is happening with the sample when it is going through a control temperature program. So we can actually control the temperature, we control the time, and we can observe, we can see what is happening, what are the transitions we are getting, and what are the information we are getting from the sample analysis. So this thermal analysis, this is spread across a different kind of sample or different kind of markets. As you see, the polymer, rubber, chemical, pharma, academia, paints. So there are wide variety of samples we can analyze with the help of thermal instrument, and we can get a lot of information from these instruments. So what kind of instruments we can, what kind of information we can get from this analytical instrument? So this is mostly the melting temperature or the heat of melting, degree of crystallinity, glass transition, softening point, curing temperature, cross-linking, oxidative stability, which is also called as oxidative induction time, isothermal crystallization, specific heat or the heat capacity, kinetic studies, moisture or volatile content, then compositional analysis, combustion, decomposition analysis, presence of recycled material, then material strength modulus, expansion, contraction, presence of plasticizers, polymer blends, its presence, its composition, and the compatibility. So there is the range is so wide that you can get a lot of information from thermal analysis. Next slide, please, Kaushik. So here we will talk, first we will talk about the TGA applications as Kaushik explained you through our what is our instrument, inside our instrument, how it works, and what are the requirements for the particular sample analysis, what are the gases are there. So we will talk about some of the applications now. So what you can expect from a TGA application. So TGA applications, you can get the compositional analysis of material, decomposition temperatures, rate of degradation, oxidative stability, evaluation of polymers, thermal stability, moisture content, volatile content analysis, then analysis of evolved gases using TGA FTIR, as Kaushik explained about our hyphenation offerings from PerkinElmer side. Then the competitive product evaluation, effect of reactive atmospheres on the material, and the determination of inert filler or the ash content. So this kind of information you can always expect or the get from the TGA applications. Next slide. So, as in the introduction, Dr. Manohar explained or talk about the applications we develop in here, Mumbai lab, as well as from our global lab. So we have variety of applications from variety of materials which can be used throughout different kind of industries. And these application notes are easily available on the internet. You can also get it, can download it, and you can use it as a reference. So here in this session, we will go through some of the applications from different types of industries and from different materials, that how our analytical instrument or how our TGA can offer you the better results and the better information. So we will start with our first application. Next slide, Kaushik. So, first application we will talk about, this is from the pharmaceutical industry, and this application will it gives an idea about the capability of our instrument, as well as how we can use this application note, or go through this application, and we can understand that how the information is important for a particular R&D center, or a particular application per person, to understand how to take the advantage of the information we are getting from instrument, and how it is critical for the particular development of the product. So here we are talking about a pharmaceutical product, that is a microcrystalline cellulose. So here in the pharmaceutical industry, particular informations from that particular sample is very much critical, because this pharmaceutical products, all the syrups and the tablets will directly impact on our human health. So they should be checked before they are released in the market. So also, this information is very much important for the formulation of this particular drugs. So if there is some problem with the formulation, with the samples, then formulation will not happen accurately, and there will be a lot of problems with the formulation, as well as that can impact on the human health. So this is this particular sample where we are actually studying the moisture content, or the volatile content of the sample, which actually gets released in the very early stage of sample analysis. So there are sample, we can run the sample in the TGA up to 1000 degrees centigrade, and we can start it, as Kaushik mentioned, we started with the room temperature, that is a 30 degrees centigrade. But here in this industry, it is also very critical. It becomes critical when the samples, most of these APIs are purified with the help of different solvents. So there is a solvent content, or the moisture content in the sample, and this solvent can be a kind of a class 1 sample, class 1 solvents. Those can be very much problematic for the human health. So we have to take care of we have to check we have to take care of that particular solvent if they are present in the samples. So here in this application note, we are trying to demonstrate that how we can capture the moisture analysis from the early stage of the analysis. So here, most of the time we start the analysis from the 30 degrees centigrade, that is a room temperature, and we go up to 900 or 1000 degrees centigrade. So here, from we try to start the analysis as low as possible with the help of simple chiller, so which can be connected to our TGA. So that can give us the chance to start early and record whatever volatile losses we are getting from the sample analysis. So here in this case, we run the sample from 30 degree, 20 degree, and the chiller with the water, which can allow us to go as minimum as 13 degrees centigrade. So uh, from the table, you can see the results we are getting. So this is the known moisture content from the sample analysis, that is around 5%. So from the table, you can see from 30 degree, it was giving the moisture loss, that is around 4%. Then 20 degree, it is slightly increased. But when we started from the 13 degree centigrade, we actually able to capture the all moisture loss which was expected from the sample analysis. So this is how this application note uh, will throw the light on the capability of our instrument, the sensitivity of instrument, and how well it is capable to capture the results from very low temperature up to 1000 degrees centigrade. So this is one of the first applications. Then we'll move to second application. Just a minute. Yeah. So we'll move to the next application. So next application is from tire industry, where the tire sample has been taken from the actual tire, and that has been analyzed for different type of things. So here, in the tire industry or in this rubber industry, polymer industry, lot of ASTMs are already stating a lot of methods there. So the methods are already given in the ASTM. Standard methods are there, and a sample should be analyzed with the help of this ASTM provided method, and result should be in the matching criteria. So here in this application note, the sample is taken from the tire sample. As I told you, this sample has been taken from the side wall of the tire, as well as the treads of the tire. Treads of the tires means the design. You can see from the surface of the tire, there is a different kind of grooves are there, which creates a kind of design there. So sample is taken from that grooves as well as the side of the tire. So these samples are analyzed with the help of our TGA. So here the instrument you are seeing is the TGA 9, and the instrument we have provided you is a TGA 8000, which is a segment upper instrument, which has more sensitivity. So here in this case, three samples are taken. Two samples are the trade sample from different brand A and brand B, and one of the sample is taken from the sidewall of the tire, that is from the brand A, and this analysis has been carried out as per ASTM method. So here, as the ASTM method suggests that the sample analysis method is, it should be hold at 50 degrees centigrade for 2 minutes. Then it should be heat from 50 to 560 degrees centigrade at the 10 degrees centigrade per minute. Then it should be cool again for up to 300 degree. Then hold at 300 degree for 2 minutes, and then the here it is asking to switch the gases from nitrogen to oxygen at 75 ml per minute. Okay, and then again it should be, the sample should be heated from 300 degree to 800 degree at the rate 10 degree centigrade. So that method has been applied, and as Kaushik mentioned, that our instrument is well capable of switching between the gases. We mostly work with the inert gas, that is a nitrogen gas, and sometimes from the polymer industry, the polymers which are containing carbon, like rubber, or maybe that can be a coal which is containing carbon. So we need to understand the carbon content of the sample also. But to understand the carbon content, we have to oxidize that sample, and we require oxygen gas there. So here our instrument actually give that kind of capability that we can switch the gases automatically. If we have to just mention it in the program that at particular temperature we want to change the gases. So here we are changing gases at 300 degrees centigrade. Okay, and when this sample has been, all these three samples has been analyzed, you can see from the results that it is giving the polymer, whatever polymer content, or we can call it as organics, that is up to from 50 to 550 degrees centigrade. Okay, and then we cool it again up to 300 degree, and we switch to oxygen gas, and from 300 to 790 we again heated the sample with oxygen environment, and here it can actually give us the percentage of the carbon black, whatever present in the sample. And at the 790 degree or 800 degree centigrade, we can take out the whatever remaining from the sample, that might be the ash or the residue or the fillers or the inorganic content from that particular sample. So here we collected the data for all the three samples. So if you can see from the graph on the third page, so it is actually showing you for the brand A and brand B trades. It is showing that most of the sample degradation is happening above the 400 degrees centigrade, and the degradation is taking care of that with the there is a slight you can see shoulder peak uh, at the left side. So that is that is what it is showing, that it is mostly the organic part is coming out from that particular sample, or it is getting decomposed. But when we analyze the side wall of the tire, it is showing that from 300 degrees centigrade we are getting the two peaks from the derivative of the thermal weight loss curve. It is giving us the two peaks. One is starting early from the 300 degree centigrade, and other is the similar as the we are getting from the trade. That is the for the organic or the polymer. So whatever we are getting here is again the carbon black also. So here what we can understand from this analysis is that the trade part of the tire is actually consist of more you can see more of the polymer or the organic substance, whereas the sidewall it contains more of the carbon black. So tire industry they have to take care of these things, because whatever trade part is mostly is in contact with the roads, and it has to be more reliable, or more, it should be long lasting. So there more of the silica part is mixed with the sample, and the sidewall of the sample, which is most of the time exposed to the sunlight or the environment. So it should actually absorb the whatever UV lights coming from the sunlight, and maintain the temperature of the tire. So that is how that analysis is actually showing us that how sidewalls of the tire is giving out the more carbon content rather than the trades which are showing more organic content. So this is how the TGA can give us the more information about this polymer, this tire industry, rubber industry. Whatever sample you are analyzing, we can actually get a lot of different those sides of the analysis, as well as the information from the analysis. Next slide, Kaushik. So next application we have taken from this lithium ion battery. So now nowadays these lithium ion batteries are more into talk, because they have a very large application, be it from our electronic devices up to the new electric cars, electric scooters. So it is now very much evolving, and as well as India is also in our country, we are most of the industries are getting into this lithium ion battery production, as well as the R&D. So here, this is the application node is based on the analysis of PVDF that is used in the lithium ion battery, and this PVDF is mostly used as a binder in the lithium ion battery, and so it actually gives us different kind of adhesion in this kind of this battery manufacturing. So it becomes very much critical to understand how it behaves, because these batteries actually get charged, and then we use these batteries charging from this battery to run our devices or the vehicles. So there is a lot of temperature barrier, or the temperature flow from this materials. So there are some materials which needs to actually uh, allow the temperature to flow, and there are some material which needs to restrict the temperature. So there should be a balance. There should be a lot of uh, uh, understanding, or the whatever understanding involved in this manufacturing of battery. So these materials becomes very much important. Their thermal capabilities, their thermal behavior becomes very much important to understand. So here this PVDF sample is analyzed with the TGA. Okay, and from the thermogram you can see it is showing two weight losses. Okay, so the first weight loss we are seeing here uh, after 400 degrees centigrade, it is mostly from the defluorination of the polymer. So it is kind of analogous to the decomposition of polyvinyl chloride, which is we call as PVDF. And the second weight loss occurring after the introduction of air. So here again, we are changing the environment of the sample analysis from inert to oxidative. We are changing from nitrogen to oxygen. Okay. And whatever the second decomposition we are seeing in this thermogram, it is likely to be from the remaining carbon, and it is showing that after it is getting decomposed, the carbon dioxide is released. So again, as Kaushik mentioned, if this instrument is coupled with our IR or GCMS, you can further analyze whatever gases coming from this sample analysis. So here, defluorination of the sample is taking place, as well as the um, carbon is also get burnt out here. So carbon dioxide is also coming, or maybe the carbon monoxide is also coming out. So these gases also can be identified with the help of our IR or GCMS if it is coupled with or hyphenated with the TGA instrument. Uh, so next slide, Kaushik. So this is it from my side, application of TGA. So we will move to the DSC part. So Kaushik, over to you.
So, ma'am, would you like to go for the TGA QA now or both after the DSC presentation?
Okay, you can continue. We can make query after finishing your presentation.
Okay, okay, no issue, ma'am. So, thank you, Sachin. Thanks for the presentation on a different kind of application which can be done using TG and the published application note or the applications which have been developed in our global lab as well as India lab. These are just for the examples, and apart from there are different applications which can be done by the TGA. So, next instrument is differential scanning calorimeter. So if you remember the chart which I shown at the beginning, that which property is being used for the DSC, that is basically the enthalpy. So this is a differential scanning calorimeter definition, where it measures the amount of energy, that is basically the heat energy absorbed or released by a sample as it is heated, cooled or held at a constant temperature. The precise measure of sample temperature is also made with a DSC. So, mm, this is a classical example of heat change in a system. So, if you consider ice, so what happens if the ice takes heat in? So, taking in is known as endothermic and releasing is known as exothermic. So, when ice is taking heat inside the system, so it's becoming water, and further the water, if is heated, it's becoming steam. The same way, when the steam is releasing the heat, is becoming water, and when it is releasing the heat further, it is becoming ice. So this is the endothermic part and this is the exothermic part. So in a DSC, we basically measure that how much heat this ice has been taken in to become water, or how much energy, the heat energy water is taken to become steam, and the vice versa. So how does it we how do we measure in DSC, or how does a DSC system works? Basically, there is a reference against which we measure the sample. So here basically we measure the temperature difference between the reference and the sample. So in reference part, as you are using in your DSC, we keep a blank pan, that is only a aluminum pan. And in the sample side, we have the aluminum pan plus sample. So when we are heating both the pans as a fixed heating rate, say 20 degrees Celsius per minute from 30 to 300 degrees Celsius. So as far as the platinum pans are concerned, there will be linear heating. There will be no change in temperature in both sides. But in the pan where the sample is there, there is some changes may occur in the sample part. So that means if any transition will happen, like glass transition, melting, where these are basically endothermic changes where the system will take the heat in, and there will be a change of temperature. The temperature will rise. So immediately there is a temperature sensor which will measure the difference between the reference temperature and the sample temperature. And this delta T value is fed into the software. The software is having its calculations and algorithms from which it will tell you the delta H, that is the enthalpy or amount of heat which has been taken in or released by the system. So this is a basically classic DSC thermogram looks like. So while heating, so if you can see, this is the x-axis, which is the temperature axis starting from 50 to 285 degrees Celsius, and this is the y-axis where heat flow endo down. That means if there is an endothermic peak, that will come downward, as because that is a negative thing where the heat is being taken, and if there is any exothermic reaction, that will come in positive part because that is releasing the heat. So here you can see two endothermic transition has occurred in a sample, which is a glass transition and then melting. And then further the sample has been cooled. So during cooling, the crystallization will happen, which is the exothermic reaction, while the system will release the heat and it will become this crystal and solid crystal. So crystallization temperature. So that is the exothermic reaction. So from the thermogram part of view, any DSC thermogram will look like this. If you run a heat cool heat session for a particular sample, and this is the working principle of the system. This is basically called a heat flux system, where there is a common furnace. So this is the furnace part where there are two position. One is a sample position, one is a reference position. Right is always the reference. R stands for reference as well as right, where we keep the blank pan, and here we keep the pan with the sample. And while heating this furnace at a particular rate, there will be some transition in the sample side. Immediately there will be a change in temperature. The temperature sensor will sense that temperature difference between the sample and reference, which is a delta T, that has been fed into the software, and from there the software will calculate the delta H. So that is the basic working principle of any heat flux based DSC. And normally all the available DSCs in the market are works on heat flux method only. So this is the model DSC 6000, which we have installed in your laboratory and you are using the system. So in this range, basically we had two model. One was DSC 6000, and another was DSC 6000. And 4000 is a very basic model with standard software which does not have any advanced features. So that is why it has been selected for DSC 6000. So that is a heat flux system or heat flux DSC system DSC 6000, where the furnace is alumina coated aluminum furnace, and the weight of the furnace is very less, 200 gram. So that is why the heating and cooling are precise and fast for this DSC 6000 system. So specification wise, this is basically a single furnace. As I shown you, there is a common furnace where the places are there to put your sample and reference pan. The measurement principle is heat flux. So I'm not going through much details into the heat flux. So that is a working principle, that is from temperature, it calculate the heat in terms of temperature. There was another technology for which Perkin-Elmer has patent, that is called power compensation technology. Due to some OEM supply issue, now that particular model has been discontinued. Maybe many of you are aware of the model DSC 8000 and 8500. That is a premier DSC model available globally and manufactured only by Perkin-Elmer using a patented technology of power compensation. But rest of all other DSCs which are available globally works on the heat flux with the common furnace where temperature difference measured and delta H calculated. But in that power compensation, the delta H was directly calculated, not using in terms of temperature. Furnace material is alumina coated aluminium, so which is a very durable, long lasting, and there is hardly any chance of oxidation, which is normally you see in any kind of other DSC furnace made of component like silver and other metal. Temperature sensor we are using thermocouple to measure the temperature difference between the sample and reference, through which the delta H is basically measured. MTDSC, that is called modulated temperature DSC, where you can do the temperature ramping, not only the linear heating, but if you want to do ramping, that is from certain temperature to certain temperature at 10, then up to a certain temperature 20, then up to certain temperature 30. So those, that is called modulated temperature DSC or step scan type of DSC. So that is possible here in DSC 6000. The software is having that, and the hardware is also having that facility. Cooling accessories, normally different chiller, intercooler, these are the common accessories are used for any DSC. So here we supplied that intercooler which can go up to -70 degrees Celsius. The maximum temperature range is -80, but that is for a particular model where this cooling system cannot be changed. That is always LN2 is needed for that operation, because that is only connected with LN2 device. No other cooling device can be attached in that particular configuration of that system. The heating and cooling rate, through software you can control the heating and cooling rate of the system 0.1 to 100 degrees Celsius, and that is you can do in the software when you are making the creating the method for your particular sample. And software is advanced, that means apart from normal DSC calculation, the additional features like kinetics, specific heat, all these are calculations are there in the software. So all the advanced calculations are added in the software which has been supplied along with this system. So DSC 6000 is basically a robust high quality heat flux furnace. Here actual you can see the image. So this is the furnace cover, and this part is the common furnace where you have two position. The right position is for your reference and the left position is for your sample, where you will in the here you will put a blank crimped aluminum pan, and here you will put the crimped pan along with the sample. So we have provided the crimper and this basically it is called robotic pan. This which can capable to take both the solid and liquid both type of sample to be analyzed in the DSC. And it's a ceramic coated furnace resistant to oxidation and chemicals. So that is the durability of our furnace, because normally if any other furnaces are made of silver, so there is a chances of getting oxidized very fast, and you need to change those furnace frequently, maybe after every 2 3 years, which is not required for this DSC 6000. This hardened nickel chromium sample plate furnace can be manually cleaned. So the sample plates which are using is made of hardened nickel chromium, that is also very durable and corrosion resistance, and also it will last long, will not affect from any kind of small spillage or anything from the sample. The furnace you can manually also clean. The service team can guide you or show you the procedure that from user end how can you clean the furnace, and you can maintain the system very well for the long run and long usage. Low mass good thermal response of this furnace. The practical maximum temperature is 450 degrees Celsius. So that is the maximum heating temperature of the furnace. But to make the life higher for the furnace, we always recommend to go up to 400. But if your the application demand, you need to go to 450, that is obvious. But otherwise, try to keep it at 400 degrees Celsius, because that will enhance the life of the furnace. The smaller furnace for better data. So as the furnace is small, so the accuracy, precision, and the heating cooling rates are much faster and accurate. So the data, that is basically the thermogram of the DSC which you are getting, will be much accurate and better. No need to worry about accidental oxidation because the construction is like that. Two mode of DSC you can do, that is a standard and modulated DSC in 6000. Normal is just linear heating rate user using from say RT to 300 or 350 degrees Celsius, and in case of modulated you can do the temperature ramping in the software for this DSC 6000. Advanced software, that is the advanced features which I was talking. So these are the advanced calculations are provided in the software, that is kinetics. That means scanning kinetics, isothermal kinetics, specific heat, purity, all these packages are included in the software. So depending on the sample type and your application demand, you can apply this kind of additional calculation, or you can do this kind of experiments in the DSC. Available for extremely low temperature, it can go up to minus 70 degree Celsius, and you can do a heat cool heat run for your samples. And due to the availability of intracooler, you can do the controlled cooling also, because the normal chiller on other things, if it is connected with DSC, so in chiller the cooling, you can do the cooling, but that is not a controlled cooling. So at what rate the sample will be cooled, that you cannot control using a chiller, but that is very much possible using the intercooler which you are using. So there you can define the exact cooling rate, that is 10 degree or 20 degree, and accordingly it will work. Despite the sophistication, it is the robust and compact, and we have globally a huge number of hundreds of installation of this DSC 6000 model. And optional 45 position auto sampler, that also is installed here in your laboratory with auto sampler, that is for unattended operation of the system. Now you don't need to give every time manually, so you can program the method and you can put the sample, and one by one it can do the analysis of the samples. So these are the different accessories and sampling which is available for our DSC 4 and 6000 45 position auto sampler, which is already there in your system. And in this UV DSC, this is a one kind of another hyphenation where UV curing is done, and then that is being measured by the DSC. So that is possible with DSC 6000. We have a option of different pans and covers. Presently, you are using, I think, standard pan, and one is a robotic universal pan with high pressure 50 microliter. So apart from that, other kind of pans like copper pan, stainless steel pan, even ceramic pans which are reusable also can be used. But normally this aluminum and other pans are not reusable because you need to crimp them, so it's a one-time use. But the pans like ceramic kind of pans, those are reusable pans. So based on the application, we have the availability of different kind of pans and covers uh, depending on your application. And then this is the chiller and intracooler, as the chiller will go up to minus 20 degrees Celsius maximum. That is also depending upon the mixture of coolant which you are using, because if you are using normal water in a chiller, it can go down maximum up to 15 degree, not less than that. And if it is a 50-50 combination of water and ethylene glycol, then it can come down to 0. And if it is a 70-30 ethylene glycol water, then it can come to minus 20. But this cooling of this chiller is not very much controlled, but it will cool the thing, but it cannot be controlled like that. But in an intracooler, which can go up to minus 70, you can do the controlled cooling of the system, and you can create the method as per your requirement. So because normally we in any DSC, unlike TGA, where we are only doing the heating cycle only, in DSC, we do a cycle of heat, cool, heat, because the first heating will give you the glass transition, melting temperature, And the cooling part, again, you can see that crystallization temperature, and the next heating you can see like for this curing studies and other thing, that whether the curing has been done or not, additional exothermic peaks are coming or not. So those kind of analysis for that, the next heating is being observed. So for those, you need to have a control heating and cooling for all the steps. And we have two kinds of crimper press. One is a standard press, which is only used for the standard samples, sample standard pans only, standard aluminum pan. But this universal press can press any kind of pans which are available with us. It may just need some kind of adapter for standard pans, but else rest of the pans can work without adapter in this universal press. So if you have the universal press, you can use any kind of pans and you can cream them in the sample and do the analysis. So that is from my part on the instrumentation and the working principle. So Sachin, you can go ahead with the applications.
Yeah, thank you, Kaushik. Thanks for going through the instrumentation and what are the offerings from our side as for the differential scanning calorimeter. So we will now talk about or discuss about the applications uh, which we can do with the help of DSC. So you can see the major applications from DSC are from again are from different kind of material, different variety of material, different kind of industries working on this material. So from polymer, rubber, or the chemical material, which is most of the time or the mostly analyzed with the help of DSC. What kind of information we can get from the DSC are kind of a melting temperature, degree of crystallinity, glass transition, curing temperature, cross-linking temperature, then oxidative stability, OIT, then isothermal crystallization, specific heat, kinetic studies, then moisture or volatile contents, compositional analysis, combustion, decomposition analysis, softening of the material, then material strength, modulus, expansion, or the contraction. This kind of information we can get from the polymers, the rubbers, or the chemicals. From pharmaceutical samples, we can always get the information in terms of moisture content, purity, packaging, then crystallinity, amorphous phase studies, coating analysis, packaging content. From the life science, we can analyze sample like proteins for the protein melting or the unfolding of proteins, protein denaturation, characterization of lyophilized proteins, or the metabolic heat of generation. So these many kind of information we can actually achieve with the help of DSC analysis from the variety of sample analysis. Next slide, please, Kaushik. So, TGA, we have developed a lot of application note or experimental notes with the help of our DSC instrument from the variety of samples and wide range of the samples from maybe it from polymer rubbers, then pharmaceutical samples, or be it pharma samples or very inorganic, organic samples. So, a lot of application notes are available for this kind of sample analysis. So we will discuss few of the applications. So the first application is next slide, Kaushik. So first application we have taken from the uh, recycled polymers. So today's nowadays, you know that lot overall the globally a lot of people are trying or the countries are trying to reuse of plastic because the plastic is getting dumped in the environment and it is not getting degraded for thousands of years, and we have to reuse it, and we have to make use of whatever plastic we are using and throwing in the garbage, so that we have to reuse again. We have to make a reuse of that. So now these industries, the recycling industries are emerging in our country also. There are a lot of plants are they are building, so they are collecting a lot of plastic waste and they are reusing it for the lot of analysis. So there are a lot of mandates are coming for this usage of this plastic. So for Now, whatever plastic products coming in the market, government trying to push the industry to use at least 30% of recycled polymer. So, a lot of manufacturers, they are started using this recycled polymers, but also they have to take care of the quality of this plastic they are manufacturing. So while reusage of this recycled plastic which is used already, that is coming from the most of the time it is coming from the garbage, so it can be contaminated also, that purity of that particular plastic substance degraded. So that needs to be understand or analyzed before it is going into the mainstream or the uh, uh, main plastic manufacturing. So as we know, there are the polymers are the virgin polymers and these recycled polymers. So virgin polymers, these polymers are pure polymers, and if they are used to manufacture some kind of products, they get into a lot of you can see you can create a good product from the virgin polymer. But when we mix the recycled polymer, the recycled polymer should be of a particular grade or should be of particular purity. So what happens, most of the plastic we are using day to day life are most of the LDP or the ADP plastic. So LDP plastic is the low density polyethylene and HDP is the high density polyethylene. So how to differentiate with this two plastics, because a lot of plastic coming from the recycling, it can be a mixture of both. Okay, and there might be a mixture of another polymer also. So as you see from the sample analysis, when we carried out the sample analysis in our DSC, it is clearly showing that for LDP, the melting and the onset temperature of the LDP is very much less than the ATP. So onset temperature is around 100 degree, and melting temperature or the peak temperature of LDP is around 111 degree centigrade. For ADP, it is onset is 117 degree centigrade, and the melting is at around 128 degree centigrade. So when we analyze our sample, we can clearly identify that whether it is LDP or the HDP. And similarly, with the help of Pyri software, we can actually put a criteria pass or fail for this sample. When we put the values for the onset and the peak temperature in the table. So for the after the calculation, it directly calculates and it shows that if the onset is above 100 degree centigrade and the peak temperature is around 111 degree centigrade, it is LDP. And whereas for the ADP, we can set the criteria as if onset is around 117 degree and peak temperature is 128 degree or above that, it must be LDP. So it can give the results in terms of pass and fail, as well as differentiating from these two closely related polymer. Most of the time, what happens that this recycled polymer that comes with the contamination of other polymer like polypropylene. So that contamination might many times it's very less, and you can see from the thermogram that it is showing very small peak after the main peak of HDP or the polyethylene. And when we zoom it, it is actually showing there is another peak there that is actually indicating the contamination from the polypropylene. So that this criteria becomes very much important for these manufacturers who are taking a lot of this recycled plastic for their product production. And this might be very much critical for some kind of plastic, because from that many pharmaceuticals are using this plastic for the storage of drugs, and after to sell these drugs, we see a lot of plastic bottles are coming for cough syrups and all these things. A lot of our food material comes in the plastic containers, plastic waste. Western. So this criteria is very much important. They have to look for this contamination, look for this purity of the substance, and from this application note, we can see it is clearly we can identify this different type of polymer which is closely related to each other, or there is a different types of polymer. So next slide, Kaushik. So next example we have taken from the solar industry uh, where again this solar cells now this industry is again booming because we are going to for to save our environment we have to switch to this clean energy, and we are mostly burning coal or diesel for a lot of energy or the electricity production. So now we are switching to solar energy, and this energy is a form of clean energy which can save our environment as well as the cost of the fuel we are burning for the electricity. Now, this solar cells, these are manufactured in many ways, and nowadays the organic solar cell or the OSCs are the new type of photovoltaic technology for converting this solar energy into electrical energy. So in this technology, generally it uses a sandwich structure of transparent electrodes, then photoactive layers, metal electrodes. Uh, among these active layers is the most important and the core component of the organic cell. Okay, and there they use this polymer and the fullerene solar cells using the conjugated polymers as electron donors, and the this fullerene and its derivatives as the as a electron acceptors. So and now these are the kind of, you can say, very uh, important research topics among the solar industry. Okay, so through the this molecular design or the strategies, on the base on these properties, the basic properties of the polymer and the fullerenes and their derivatives, they need to be optimized. Okay, because one is the electron donor and one is the electron acceptor. So their properties should be thoroughly examined before they are going into the production. They have to look for that there should be a proper percentage for this of this two material to uh, to work properly. Okay, so it is also then that the crystallinity of these active materials are and their regularity of their molecular arrangement, it becomes very much important for this to for the solar cell to work efficiently. Okay, so this material has been taken for the analysis, and a different ratio of this organic material, that is sorry, organic polymer, that is we call it as DBT, and the fullerene samples. So there are the different mixtures or the different concentration has been taken, and those has been analyzed with the help of our DSC. Okay, so what actually we do here is that here we actually take a different percentage sample and we analyze with the DSC, and you can see from the curve it is giving a different kind of concentration of the peak or the height of the peak, which shows there is a different enthalpy values, but their melting temperature are matching, but it is showing different enthalpy values. Okay, as the concentration of these two material are changing. Okay, so they are giving different peak shapes here. Okay, so different or the different strength of the enthalpies. So that enthalpy will tell us about the magnitude of the cell's energy conversion efficiency. Okay, so this is how these samples with the different concentration or the different percentage can be analyzed with the DSC. Okay, and here in this DSC, this test will give us the heat curve of this active layer material in an organic cell, and the enthalpy of melting is this is calculated based on the melting peak. Okay, and it can be and it help us to determine the molecular alignment and the compatibility of the material. Okay, so this is how it becomes very much important for this solar industry. Um, Researchers or the manufacturers to get this type of information to manufacturer or to select the material for their final product. Okay. And next slide, Kaushik. Okay. So the next application we have taken from the pharma industry again. Okay. So the again, as we know, this is pharma industry is very kind of sensitive industry for the sample they are analyzing at their labs, because this sample or this material are directly related to human health, and they need to be examined thoroughly before they go into production, and before they select it for the further analysis. So this application note, it actually tells us about the polymorphism within the pharma samples, and how we can actually find, or we can detect the polymorphs of this particular sample. So the polymorphism is a term used in the pharma industry for their APIs, that is active pharmaceutical ingredients. These APIs can exhibit two or three polymorphs. So two or three polymorphs means they exhibit two or three organic structure, or the uh, you can say they can exhibit forms of their structure. So they are very closely related to each other, but one of the these two or three forms, one is only clinically active. Okay, so that will be work for the disease. So other forms are not active clinically, so they are not used for the uh, formulation of the drug. So they have to select a particular form. Now these forms, so as we know, there are two or three forms are there. So these forms are, they exhibit different melting temperature. But sometimes what happens, these melting temperature are so close to each other that when we analyze the sample, it gives a single melting peak for all the three polymorphs. So in this case, DSC is the instrument which can give us the advantage to run the sample at lower heating rate. So when we run the sample, we analyze this sample with the regular heating rate. It is giving the single melting temperature. But when we observe it closely, it is showing us a slight uh, very slight shoulder peak when it is ending at the right side. Okay, so when we analyze this sample with lower heating rate. Okay, so here the heating rates are 10 degrees centigrade, and after that we run this sample or analyze this sample with the 3 degrees centigrade of heating rate. So at the 3 degree centigrade, actually it is showing there are two peaks. Then when the first peak is ending, it is again when the melting is ended, there is a second peak it is showing for the endothermic reaction. So it is actually separating out the two polymorphs, and then we can select that is which is the polymorph 1 and polymorph 2, and which one has to be selected for the final formulation. So this is how the DSC instrument can work in that particular level or that particular sensitivity to understand that those small changes happening with the sample, and can provide us the very vital information which can be very critical for the final formulation. Uh, so this is it from my side um, for the applications of DSC. Over to you, Kaushik.
Yeah, so thank you, Sachin. So that's from the presentation part, madam.
Okay.
So now you have any
Um,
queries?